Thank you everybody for being here today. My name is Brent Griffin, and this presentation is called Zero-Shot Coreset Selection via Iterative Subspace Sampling. And this was work originally presented at WACV, along with everyone else here. So please see the paper for this talk for any additional details, along with all the other talks. It's a pleasure to be here for the meetup. And the motivation for this work is pretty straightforward. In the last talk, we heard about how models are continuing to scale increasingly year after year into billions and billions of parameters. And along with that, they need to train on increasingly more and more data in order to be more performant. But with that data and scale comes a hidden tax. And that's the cost that it takes to label all that data, but also the wasted time spent training on redundant images. On the other hand, what if we could eliminate 90% of our data set before we ever spend a cent on labels or even a second on training our models? This was the promise of Coreset selection when the problem was first presented in the literature. And ZCore, our method, is a state-of-the-art Coreset selection approach that requires absolutely no labels or training on your candidate data. So as an additional motivation for this work, let's think about robotics and autonomous vehicles. These systems are inherently data abundant, but they're label sparse if you have any labels at all. So if we take the HSR robot on the left, which is from the lab that I had at University of Michigan, it alone has 4 different sensing modalities that bring in visual information. And even that robot just operates for an hour. That's bringing in just an immense amount of visual streaming data. Now, this is important because the robot can make observations about its environment, find new objects, track how the environment is changing. It can even explore new environments. And what we want to be able to do is go through that data and find, okay, what are the examples that we need to be able to bring into our model training regime so that the robot can continue to be successful at the tasks that it is performing. On the other hand, if we think about how robotics would actually be deployed out in the real world, you're going to have dozens or potentially even hundreds of robots or AV systems being used in the fleet. And they're not going to be just operating for an hour. They're going to be operating for days, weeks, or potentially even months at a time. And so if we think about the aggregate streams of data coming together from all that robot experience that's out in the world, we can envision this stream as a data dragon, which is shown on the right. And this is just absolutely untenable. We can't possibly train on all that data, let alone label all that data. And nonetheless, what we've seen is that recent Coreset selection methods have increasingly had a large startup cost just to do Coreset selection. So for example, I'm going to talk about some methods that require that you label all the data before they perform Coreset selection. Or there are other methods that require that you perform self-supervision on every example before you do Coreset selection. And this is somewhat paradoxical because the whole point of Coreset selection is to save your resources by selecting a smaller data set. But these methods are asking you to first spend your resources to save those resources. And so this is just a mismatch if we think about physical AI today in these fleets of robot and AV systems. And this is the bottleneck in physical AI development. We're essentially drowning in data, but we're starving for the right subset to train on. And so the motivation for this work is how can we go through all that data in a very low cost way and a fast way and find those examples that are important to update for our model training pipeline. So just to look at some of the specific Coreset selection bottlenecks in literature, and I want to be clear, each of the methods that I'm talking about are innovative and technically sound. I just think that there's a bit of a mismatch for the assumptions that they make, and that essentially is limiting applicability to the robotics and autonomous vehicle and scaled physical AI implementation that this work is really motivated by. So anyway, getting into more of the specifics, temporal dual depth scoring was originally presented at CVPR in 2024. And what they do is they assume that when you're going to go and select your Coreset, basically all the initial data set is labeled. They train your model on that entire data set, and then they look at what are the gradient contributions of every single example throughout the entire training process, and what is the minimum set of examples that we can use to replicate those gradients on a per epoch basis by without having to have like the full set of examples based on the individual contribution of all those. How can we make the projected gradient with less examples? Now, this is technically very sound, but it does take a lot of time because you have to train on the entire data set before you do Coreset selection. You then have to go through and siphon through all those gradient dynamics of the individual examples. And again, it requires that the data are labeled before you even perform Coreset selection. And so this isn't really a good match for the idea of being able to operate on the world's data and not having to spend a lot of money to figure out what core set do we want to be able to use. The other thing that I'll mention, and I think these kinds of things can be common in academic or the research world, is they absolutely pursue the best performance possible on benchmarks. And in pursuit of that, they do per data set and prune rate validation tuning. So what this means is their algorithm has different parameters that you can set, and they test a whole different slew of them. And then they look at which ones perform best on the actual validation set that they're reporting for their benchmark. And then after the fact, they say, okay, these are the settings for this algorithm, and this setting, this data set, this prune rate. But this isn't practical, again, if we think about, implementing a robotics or AV system. We don't get to pause time and look at what version of our core set operates on the data that we're handling at inference, let alone we don't even have that data that's labeled. And so again, this limits generalization if you want to be able to use a solution like this out of the box quickly. Now, another method that was presented last year at iClear did a good job because they eliminated the requirement for labels. And the way that they did this was they basically took the entire unlabeled data set, they processed it through a vision encoder, and then they took the embedding space and they performed what they call deep clustering. Now, in each one of those clusters, they're going to apply a pseudo label and pretend that that is like ground truth. This is the class. And then what they can do is they can train models on those pseudo labeled classes, and they get training dynamics from the actual data set. And then they use these to select their core set. So this is a big step forward in terms of eliminating the need for having all your data labeled. But now that we are actually creating a pseudo labeled data set and then training on that data set, it actually takes more time in terms of compute. Additionally, although they don't do data set and prune rate specific tuning on the actual validation set, to their credit, they have a holdout set from the pseudo labeled data set. They still do data set and prune rate tuning. And so they actually run several different configurations of their algorithm to figure out which of these versions is going to perform best, given the data set that we're operating on and the prune rate that meets our budget. And so this, again, limits generalization. And I'll also mention that there's a little bit of a hit in performance that this method finds from the core set in terms of downstream model training relative to TDDS, because it's using a pseudo-labeled version of training and those corresponding dynamics. Now, fast forward to this year, at WACV back in March, we presented this work, ZCore, and this is the only state-of-the-art core set selection method that doesn't require any labels or training. And because it doesn't require any training, and it's a relatively straightforward algorithm, which I'll get into, it's actually very fast. And then additionally, it's generalizable because in our benchmark experiments, we use the exact same settings for the algorithm itself across all prune rates and all data sets. So it essentially lends itself to being used out of the box because there's a single setting that we find works well across all the data sets that we test, whether it's satellite imagery or web data that you see in ImageNet. And then this is really being built now for a core set selection method that you can actually use at the scale of robotics and AV systems, which was the whole goal of what we're trying to do or what this work is motivated by. And so we can finally kind of tame that data dragon and find those meaningful examples without having to have a bunch of upfront costs just to find the set of data that we want to use or invest in for our model training pipeline. So with the problem of core set selection motivated, I'm next going to be talking about the actual ZCore method. I'll have some experimental results where we compare to about a dozen different state-of-the-art core set selection methods from the literature. I'll talk about different ways that ZCore can be configured. Now, again, you don't have to change any of the configuration, but there's actually some interesting insights that you can find when we look at different ways you can implement ZCore, and it still performs pretty well. And I'm also going to talk about how you can ZCore your own data today. And then I'm happy to answer any questions that are remaining at the end of the talk. So with that, let's dive right into it. The first step of using ZCore is we take all these unlabeled images that are coming in from our robotics or AV systems, and we're just going to process them through an off-the-shelf foundation model. And this is going to create a high-dimensional embedding space representation of the unlabeled data. And so now we don't have labels, but we do have a feature embedding that's going to be activated in different ways based on the foundation model that's already been trained before we even started this work. Now, the default embeddings that we use in the paper are concatenated clip and resonant 18, which makes an embedding space that's about 1,280 dimensions. But we also show that you can use a variety of embeddings, and the method and everything I'm about to talk about still works relatively well. So this is a process that you just perform once, basically a single forward pass on each one of the images. And then from there, we do what we call iterative subspace sampling. And what we do is we take this high dimensional embedding space representation of the data set and we slice it into subspaces that are randomly chosen. So we have M random dimensions that we choose from the full embedding space. Our default configuration is to just randomly select 2 of those dimensions. And so we're creating these 2D slices of that high dimensional embedding space. And we do this for 2 reasons. The first is that it generates about 1 million unique subspaces that each emphasize a different combination of features. So if you were to perform some importance scoring on the full embedding space, what can happen is the different dimensions have different senses of scale. And so what that can do is it can kind of upset how much your algorithm is going to emphasize certain features versus others. In this way, when we slice the data set and we're performing importance scoring on those slices, we're making sure that each one of the dimensions of the embedding space kind of has its say at different times and in different combinations with other features. The other thing that this does is now that we're operating in a 2D space, all the operations that we do to determine which examples are important or not are dramatically simplified. And this improves runtime quite a bit so we can actually operate at the scale of robotics and AV data. Okay, so once we make the slice, we're going to have a 3-step process that we do to then end up scoring the examples in that slice and across the whole data set. So for each slice, we sample the subspace via triangular distribution. And you can just think of this as we generate a distribution that's representing that slice of the embedding space, and we're just going to sample a point, and we're going to say, okay, these are the regions that we care about, and we're going to sample this over and over. Now, the reason why we use a triangular distribution is because compared to a Gaussian distribution or a uniform distribution, it alone covers dense regions of the embedding space while also sufficiently covering the outliers that are kind of at the fringes of those slices of the embedding space. If you look at the figure in the top right, we have examples of an embedding distribution for both ResNet and CLIP. ResNet 18 is on the left, CLIP is on the right. And what you find is the uniform distribution kind of undersamples the areas where you have the most examples, and it oversamples the areas where you don't have that many. And so you're kind of oversampling this area that is maybe not as relevant for making distinctions between different areas of your data. On the other hand, the Gaussian distribution does sample the dense region of the embedding space really well. But sometimes if you look at the example on the left with ResNet, it's actually sampling empty space. And it's also not really capturing the data that exists at the fringes. Now, you can use either of these distributions. And again, the algorithm's fairly robust. They'll still work pretty well. We just find that using a triangular distribution specifically ends up giving us the best, most reliable general performance. Okay, so now you've sampled this point in 2D space. And we want to provide a reward for the closest existing example because it's basically representing the space that we're sampling, the space that we care about in that slice really well. And so we provide this coverage reward. And what that does is it basically is promoting this example that's in the regions or in the areas that we're sampling that we care about a lot. Keep in mind, as we're sampling a space. And so this is looking at an actual example that's closest existing to that. Now, there's another thing we do besides promoting this example by adding a reward, and that's we then subsequently look at the nearest neighbors of that example, and we add a redundancy penalty. And this is done to the nearest neighbors to make sure that we're not over-promoting one region of the data set and including a bunch of redundancy. So if we're promoting one example, we're going to demote the nearest neighbors so that we don't have a bunch of redundant information as we're going through and selecting which examples are we going to be using from the data set. And so that's basically the 3-step process that we use after we slice the full embedding space into these slices. And it's just step 1. We're going to sample the subspace via triangular distribution. We're going to add a coverage reward to the closest existing example. And then we're going to add a redundancy penalty to its nearest neighbors. And we perform this iteratively across a whole bunch of combinations of subspaces. But the interesting thing about this is when you think about the big picture of how this algorithm works, we only need to generate the full embeddings once. And then each one of these iterative subspace steps, the sampling, the coverage reward, the redundancy, they're not only simple in this 2D space, they're also parallelizable. You can perform every iteration in parallel if you have the compute to do it. And this makes the algorithm very fast. And a lot of our tests are done just even on a standard laptop. So you don't even need that much parallelization to make this process operate really quickly. Okay. So with that, after we do the iterative scoring, we now have a score that's going to apply to every example in our data set. And so now the data set has an inherent rank. So then if you had 1 million images or data examples to start with, and you had a budget of 100,000, we simply select the top 100,000 examples, and now you have your core set. If you double your budget and you have 200,000 examples, we just select the top 200,000 examples. And so in this way, we use the same score without any kind of prune rate specific tuning. And so this also helps make the model very general, or the ZCore approach very general when we're doing core set selection across different data sets and different prune rates. So that in essence is the sum total of the method. There are, of course, plenty more details in the paper, but in summary, ZCore is a method of core set selection that doesn't require any labels or training. And because of this, it's very fast. And it's also fast because we reduce the dimension that it's operating in, and it's also parallelizable. And so it can take advantage of basically any amount of compute that you have to do this core set selection process very quickly. It's also very generalizable. We find that we can use constant settings across all the data sets and prune rates, so you don't have to worry about it being over-parameterized or over-designed for any specific data set or prune rate. Now, if we're going to look at some of the actual results, we have the good. These are the examples that ZCore has selected to be a part of the core set. We have examples shown in the top from Eurosat, CFAR 100, and ImageNet. And what we find is that the top performing examples and the ones that ZCore ranks the highest basically have a pretty good diversity right from the outset, if you look at the top 10 examples. And as you expand that threshold, and I'll have an example of this later, you continue to see that it actually pulls really representative data from the data set before it ever really repeats itself. Now, on the other hand, at the bottom, we have the bad. These are the scores that are being ranked very low by ZCore. And what we find is if we looked at the lowest scoring example on the bottom left, and then look at its nearest neighbors, in all cases, regardless of data set, this example is highly redundant and doesn't really offer any new information to the core set. And this is why ZCore is saying that this is not a valuable example to include. So we've talked about the good, we've talked about the bad. Now let's talk about the ugly. And this is the runtime and annotation comparison with those other state-of-the-art core set selection methods I mentioned earlier. So we find in our benchmark experiments that ZCore runs 28 times faster than TDDS on a laptop and 40 times faster than ELFS on a GPU. Now, the reason why we don't have laptop comparison is because of hardware requirements. We couldn't even get ELFS to run on our laptop that we use for these experiments, but we still have the comparison on the GPU. ZCore is still much faster. But the real kicker here, or the real benefit, is the third bullet. And that's how we use 10 times fewer labels than TDDS when you're operating with a core set that's a 90% prune rate. And the reason for this, again, is because TDDS requires that your entire candidate data set be labeled before it selects what your core set is going to be. So you already had to label all of your data examples. On the other hand, ZCore makes this determination of core set without having any labels, and you only need to provide labels after the core set is selected. And so in this way, we save basically 1.15 million fewer labels when we're operating in this regime on ImageNet. Now, none of this cost savings in time or annotation matters if your core set isn't actually performing. So we also do a pretty exhaustive comparison of how these methods work in terms of the downstream model performance. And what we found is that ZCore outperforms all the state-of-the-art label-based methods and unlabeled methods, with only the exception of TDDS. And this is especially true at low data rates. So if you look at the plot below, we have downstream model validation performance after selecting a core set for increasingly smaller and smaller core sets. So on the left, we'll have 70%. On the right, we'll have 10% of the data set being used. And what we find, whether it's CFAR 10 on the left, CFAR 100 in the middle, or ImageNet on the right, is a majority of core set selection methods don't really operate in this low data regime that well, and the performance of their core sets drops off pretty substantially. But this is exactly the area where you stand to gain the most performance in terms of cost and the time that it takes to select your core set and the time that it takes to train your model. And we also find that when we look at ImageNet performance specifically at a 90% prune rate, not only does ZCore use 1.15 million fewer labels, the data set that it selects as its core set actually outperforms TDDS. And so in this one case, you kind of get a have your cake and eat it too, and that we're getting the top performance, and we're not requiring that you label your data just to select from it, and we're not requiring any pre-training on the data. So with that, I wanted to talk a little bit about some different ways that you can configure ZCore. We have a whole bunch of different exhaustive tests for alternative configurations that you can find in the paper. It's available today from the Computer Vision Foundation Open Access if you follow the link here. But the first one I want to talk about is one of the comments that we got from reviewers is, okay, fine, like ZCore is not using any labels, but what about the foundation models that you trained on, ResNet 18 and CLIP? Those use labels for training. So your process in theory is using labels. And that's an okay point. Like we can put aside the fact that those models are trained anyway and already exist. And what we found is we can use a completely self-supervised foundation model like Dino V2, use those embeddings, achieve a completely holistically, theoretically, absolutely unlabeled implementation. And the performance is almost equivalent to when we use the ResNet 18 and CLIP concatenated embeddings. The other thing I wanted to point out, or that came up during review process, is okay, but what if you use an alternative embedding dimension reduction technique? Because maybe this random slicing of the embedding space was maybe a little bit non-intuitive. And so we went ahead and we tested it. If you use PCA or TSNE for the embedding reduction from the full high dimensional embedding space down to a lower dimension, and then you still do all the same, like corresponding ZCore processes after the fact of sampling with a triangular distribution, determining a coverage reward, penalizing redundancy, you still get nearly the same performance that you do with the slicing method. So if your data set was already processed through embeddings and put through PCA or TSNE, you could still use these and then just use the downstream ZCore processes from there, and you still be able to find a performant core set. The last thing I want to talk about in terms of ablations or alternative configurations is that for the algorithm itself, we do test a range of different settings. And in the example of the redundancy penalty, we can do things like change the number of nearest neighbors. And what we found is that you can change these parameters over an order of magnitude lower or an order of magnitude higher, and you still get very close to the optimal configuration performance. And I think this says a couple things. One is the algorithm itself is very robust to these changes in parameter setting, which is also probably why we can just use the same setting across all data sets. But on the other hand, what you're really doing when you do something like change the number of nearest neighbors is you're changing the ratio of neighbors that you are penalizing relative to the size of the entire data set. And so this simultaneously explains why ZCore works across such a wide scale of different data sets, whether we're talking about a very small split of Eurosat that we have in the paper, that's a couple thousand images, all the way up to ImageNet scale image data, which is over 1 million images. So with that pointed out, I'm going to get to closing here soon. I did want to point out that ZCore is fully open source, so you can ZCore your own data today. We'd be very interested to know how it goes. It's available natively within 51. You can also follow the QR code here and replicate all the experiments that we have from the paper. And we do have customers are using this in their own workflows today, which is very exciting for us. And I also just want to show a brief demo. So I showed this HSR robot earlier from when I had my lab at the University of Michigan. And I was able to collect data while I was there in a variety of buildings from a variety of sensing modalities. There's some gripper camera, some overhead like head camera that's looking at different scenes. I can load this into 51. I can push them through ResNet 18, which is very quick in terms of embedding generation. Look at the embedding space and then run ZCore as well and look at which of these examples is actually getting a high score from ZCore. And what you can find is that you're going to get these examples that are representative from these different little modes of data collection that the robot exhibited, regardless of what building it was in, what objects it was interacting with, what environment it was in. And then you can decrease that threshold of ZCore and get more and more examples and build your data set. And it takes about the time that you see here once you get everything running within 51. And you can find that each one of these different areas that are representing different tasks the robot is doing or different environments are well represented. Okay, so in conclusion, ZCore is a state-of-the-art core set selection method. It doesn't require any labels or training. Because of this, it's extremely fast. There are also some algorithm tricks that I talked about earlier, like the subspace slicing that make it even faster. Basically 28 times faster than the competition when we're looking at a standard laptop. It's also scalable. We have proven success from robot collected data, the CFAR 10 or 100, to ImageNet, to these smaller data sets with Eurosat, and it's completely open source. So you can use this today on your data. You don't need any labels. You don't need to train on the data. You can use ZCore out of the box. I'd also like to acknowledge my co-authors on the paper, Jacob Marks and Jason Corso, who were a huge amount of inspiration and help throughout this whole process, as well as Voxel 51, which makes this great platform that we're able to use ZCore within. And I also just want to say briefly, Peter Muller, machine learning engineer at Voxel 51, has been kind of taking the reins on this project. And he's been finding that when we look at unbalanced data sets specifically, the benefits of using ZCore are even more apparent. And he's also finding other, let's call them indicators, that you can use to create even better core sets without any labels or training on your candidate data. So please use ZCore today. Also be looking for ZCore++ in the future. And with that, I'm happy to answer any questions that you may have.